These are notes for day 7, and we are looking at graphs of logs. So we've done this before where we've looked at graphs of specific functions, and then we underwent transformations. We're going to do the same thing here. But first we need to look at graphs of just like a parent function, a parent type of function. So before we jump into logs, we are going to look at the exponential function 2 to the x. So, and we're going to look at this through our graphing calculator. So if we look at, that function 2 to the x, that's just real quick completing the table here. This would be 2 to the minus 2. This would be 2 to the 0, 2 to the first power, right? We could fill in this table. This would be 2 squared. This would be 2 cubed. This would be 2 to the 4th, right? That's what an exponential is. These are the powers, and of course the f of x is the answer. And so, we could even, this is 1, this is 2, this is 4, right? We could even fill in this table without even graphing it. That's 8. So this must be 16. We could even fill in that table without graphing it per se for this exponential. But I am going to graph it on my graphing calculator. So let's grab this, make it blue, type in 2 to the x power. So remember, that's the caret key to get up into the power, and then the variable key x. So it looks something like that. Then we can just grab those points. So we have when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. When x is 4, y is 16. Right? And then I didn't fill this in 2 to the minus 2. I'm going to grab the table here, and let's switch this over to auto. 2 to the minus 2, if you notice, is 0.25. So this is 0.25. In other words, it's 1 over 2 squared, which is 1 over a quarter, right? And that's the decimal equivalent. So 2 to the negative 2, here's negative 2. We're down here at 0.25. This is 0.5 if you want to know. So we have something that looks like, let's see if I can get something pretty decent graphed here. It looks like that. Let me redo that. And it's getting closer to the x-axis because the x-axis is an asymptote. And then it's growing by powers of 2, so it's growing super quickly like that as we get into the positive x. So that is y equals, that's our exponential 2 to the x. Okay? And so now let's consider something a little less obvious, and that is log base 2. So now what we're going to consider is this log base 2 of x. Now, we're going to make a table of that too. Oh, actually, before we make a table, let's fill in this information. Right, the intercept is 0, 1. The domain, the x values that we use are all real numbers. So we're using all of these x values. And the range is, we're just using the positive y values. So that range is y greater than 0, excuse me. And then that makes writing the asymptote easy, because the asymptote is just what you see for the range. It's just change it to an equal sign. That's the x-axis. X-axis, right? That's what y equals 0 is. Okay. So now looking at what we're talking about here, that's an exponential, right? That's powers of 2. 2 is called the base, which is why we when we talk about the equivalent logarithmic function, we call this log base 2. Log base 2 of x, right? That's what that's saying. Now, your calculator only can do base 10, powers of 10. So this is powers of 2. That's what that is. And so since your calculator can't do log base 2, you have to convert that into a log base 10. And the way they do that is, we call this the change of base, right? Log base 2 of x is equal to 2 log base 10 of x over log base 10 of 2. And of course, we don't have to write base 10. That would just be log of x over log of 2. So that's what we have to put in for our logarithmic function. So y2, let's make it orange. And I'm going to put in log log. Log is right here next to the 7 key. So it's log base 10. So of x, there's my variable. I'm going to close that bracket, divided by. And then I'm going to go log base 10 again, log. And log base 10 of 2 is just a number. It's 10 to what power? It's what power of 10 do we need to make 2? It's a decimal. And so when I graph that, we get something that looks like that. Notice that those graphs, if I zoom out far enough, let me make this bigger. We talked about inverses, right? And we talked about the line y equals x. Let me graph that. Here's y equals x. Let's make that gray. We see that it's a reflection over the line y equals x. So we know that log base 2 of x is the inverse of the exponential 2 to the x. So this is the log base 2 of x is the inverse of the exponential y equals 2 to the power x. So we know what happens with inverses, right? We swap the x's and the y's. So let's take a look at that in the tables. So notice we have an x value in our table of 8. Right here, x value of 8. So I'm actually going to do the table because we're talking about a couple of different things, I'm actually going to do an ask. So an x equals 8 gives me a log of 3. So this is 3. And notice that they are swapped in the exponential table. 3 comma 8, this is 8 comma 3. What happens when I have an x value of 4? X value of 4 gets me a log of 2. So again, notice that is, whoops, I'm squaring out the wrong one. That is swapped in that exponential table. 4 comma 2 is 2 comma 4 in the exponential table. So what happens when x is 1, whoops, hold on here, there we go. When x is 1, we get 0. And when x is 1/4, when x is 1/4, so it's 0.25, we get -2, right? Remember that negative power in our exponential table? So now what happens is these are the powers. These are the powers of the x values, right? Just like above, the x's were the powers of the y values. So there's that swapping that takes place. And so if we graph this, it's 8 comma 3, 8 comma 3, which is right there. That's 8 comma 3. And that's 4 comma 2. It's right there, 4 comma 2. And we have 1 comma 0. We have an x-intercept instead of a y-intercept now. 1 comma 0. And we have a quarter comma negative 2, right? That's a quarter comma negative 2. 1/4 comma negative 2. Those are all inverses of these points on the exponential function. So I should be able, I don't have it in the table, but I should be able to go out to 4 comma 16, right? So that would be way out here. So we have something that looks like, let me see if I can get this drawn accurately. Now notice we have an asymptote, but the asymptote is the other axis now because they've swapped. And then it's like that. So notice that the y-axis is now an asymptote, not the x-axis. So the asymptote now is the y-axis. And the equation for that would be x equals 0. We swapped the x's and the y's. The range is all reals. So think about, the range are the y values, right? And we're using all of these y values for that logarithmic function. So it's, the range is now all reals. And notice the domain, the x values. The x values are just these positive x values. So the range is now x greater than 0, which means I can't have any negative x values. So think about that. And I'm going to show you that in this mode here. If I take the log of negative 3 divided by the log of 2, because I have to get it back into base 2, log of 2, it tells me on my calculator screen that I get an error. It can't calculate it, okay? And then we can see that in the graph. We can see that in the graph that we can't use negative values of x on logarithmic functions, just like we don't get negative values on exponential functions. And then in this case, it's an x-intercept of 1 comma 0. So we have this definite, we know they're inverses because this is all being, we're swapping, this is all being swapped. Swapped x and y, swapped ranges and domains. So we know they're inverses of one another. So so as a result, we can't have, this is an error, okay, and this is an error, because those locations on the graph are inaccessible. We can't get to 0 on the x-axis, and we can't get to negatives on the x-axis. So, taking a look at the questions, and I think I'm going to make the graphing calculator go away. There we go. Taking a look at the these follow-up questions here. It says use the values from the table, the graph on the plane above with f of x and complete the column for g of x in question 1. So we did that. Add the line y equals x to our graph. So we talked about that. If we add the line y equals x, I'll add that in gray like it was on the graphing calculator. Y equals x is where x's and y's are the same, right? 5 comma 5, 10 comma 10, 15 comma 15, 0 comma 0. If we add that line y equals x, then we can notice that our exponential and our log of the same base are inverses of one another. They're reflections. So this is our reflection line, as we've seen several times with when we talked about inverses, that reflection property we get. So they are inverses. So y equals 2 to the x is the inverse of y equals log base 2 to the x. That's why we call it log base 2. The big 2 over here in the exponential is also called a base. Remember we talked about that a couple sections ago, where 2 is the base, x is the power, y is the answer. So these all switch. we switch, oops, I think I spelled that wrong. Let's get rid of that whole thing, switch. We switch the x and y in those functions. So, and the other way to say that is inputs become outputs. So if we talk about inputs, x's, outputs, y's, right? Inputs become outputs and outputs become inputs. So now really what we're focusing on is, we know these are inverses. We know exponentials have a certain curvature shape. It's very distinct, whether it's growth or decay. So do logarithmics. They have a certain curvature that's very distinct. They have asymptotes and all those things that we're going to kind of keep track of. So the learning targets then is, the first learning target is how to graph a logarithmic function. So graphing is our first learning target. So in general, just to get that distinctive shape here, we have our coordinate axes. So this is our x, this is our y, and we know that let's talk about graph of the parent function. Parent function. Okay, we know that, just going back up here for a second, we know that in the logarithmic function, these are the powers, the outputs are the powers. And so when we're talking about graphing this, basically we're saying we have an asymptote, so we're gonna, the parent function, the asymptote is gonna be this y-axis. So that's gonna be our asymptote. And then we're gonna have over 1 is going to be our intercept, so our x-intercept is 1, 0. We know that this is going to curve down closer to that asymptote. And then we're going to count out by powers here. So we're going to count, if we have, for instance, log base 2 of x, if we take a look at that back up here, notice we're starting here, and we're looking at, this is the second power of 2, this is the third power of 2, so these powers become our y values here. So if we're talking about log base 2 of x, then 1, 2, 3, 4, that's the second power of 2 is 4. The first power of 2 is 2. And so we have, I wish I would have a little more space, but we can see that if this parent function was log base 2, then this would be, this is 1, 0. This is 4, 2, and so on with that pattern. We have 8, 3, and so on and so forth with that pattern. We'll be looking for that specific 2 to a power pattern on the x-axis. And so the other learning target, number 3. Oh, this is 1 and 2. Shoot. Okay, this is 1 and 2. Let me get a little more specific about what number 2 is. If we want to transform, so learning target number 2, I didn't see it, they combined them, is transforming this. And so if we transform this, then let's move this over and say this equals y. And maybe the domain, maybe add that the domain is all positive x's and the range is all reals, right? We're flipping the exponential information. So if we want to transform this, if we want to do a transformation, then we are going to, I'm just going to stick with base 2. We are going to put the similar transformational information in. So we would have x minus h plus k. And we're just going to stick to horizontal and vertical transformations. We're going to just stick to sliding this. We're not going to worry about the a and all that stuff. Not for this section. We're just going to worry about translating it horizontally and vertically. So if h is positive, we go right. If h is negative, we go left. If k is positive, we go up. If k is negative, we go down. All that stuff that we were doing before. Learning target number 3 is that they are inverse functions. So in general, we know that inverse functions are mirror images about the line y equals x, right? So if I could graph the line y equals x, I think I have to slide that over a little bit. There we go. Then our logarithmic function is going to have an intercept and an asymptote that's vertical, and our exponential function is going to have a y-intercept and an asymptote that is horizontal. So it's going to look like this. So this is y equals 2 to the x, and this is y equals log base 2. Those have to match of x, and those are inverses of one another, and so we see the swapping of the x's and the y. So as you look at the check your understanding, it says use your graphing calculator to graph each function, and so just a couple of things to acknowledge is, one, we're going to let you use a calculator to graph. But basically we want to see that pattern based on, this is base 3. Okay, so we're taking, that means 3 to a power. So when you're graphing your points, we want to see that pattern of taking 3 to a power on the function. And then these are this is a transformation where we could actually write this as y equals log base 3. So you can have that 3 pattern again, x minus 4 plus 2, right? There's your h and k. So we know that this goes up 4 and right 2. So, and then we have to adjust the domain and range and the asymptote. We have to slide all of that with it. So do the check your understanding and check your answers in Blackboard before you go on to the homework, which is drawing transformed functions. And again, we're just going to slide them horizontally and vertically, which means when we get to, we're going to skip 9 and 10 because of this stuff. It's a little more complicated. And 11 and 12, we're going to skip those. You can graph them just to see what's going on there, but